Here's an introduction to circuits. So what I've drawn here is a wire, and inside that wire there are lots of electrons that are free to move. Now they're not moving anywhere in particular at the moment, they might be jiggling around a bit, but if we apply an electric field on this by putting a negative charge at this end and a positive charge at this end, those electrons are all going to feel a force away from the negative towards the positive. So you're going to get a lot of net drift in that direction because of that applied electric field. What we're going to do now is essentially what happens in a circuit. We're going to take this negative and bump it up against the end of the positive and bump it up against the end of the negative and create a circuit. And I'm going to draw that with the negative at one end, the positive at the other. This is the negative terminal and positive terminal of a battery, and join it up into what we call a circuit. And if we draw it like this, we've got basically a wire joining up the positive and the negative end. Now positive is longer, the symbol is longer than the negative. We've basically got one wire which is attaching the positive and the negative ends of the terminal. Now we know that electrons flow from the negative end to the positive end, so I'm just going to draw in electron flow going that way. Now, in a very strange way, and it's an accident of history, electron flow is actually the opposite direction to what they thought the charge carriers were moving. And so from the beginning of time, and still to this day, we use something called conventional current, which can be thought of as the way that positive charge carriers would flow if they could. Of course they don't, so it's just the opposite direction of the electron flow. Now of course circuits don't just have a wire around them. They actually have, if that happened, it would essentially be a short circuit, and things would get very hot very fast because a lot of energy would be dissipated just in the wire very quickly. Large currents would flow, and we'll talk about that later. So what we're going to do here is put in a symbol for a resistor here, and that's just a rectangle, or it could be any thing that we call a load. So in this case it's a resistor, but we could have another load of any type, such as a lamp or a motor, something like that. Now if we were to measure the potential difference across the battery or the cell, that I've drawn here, we would find that the electrons going in here would have a lower potential energy than the ones coming out here. And we know that from the definition of potential difference, which is the work done per unit charge, we can also write that as it's the amount of energy, or the change in energy per unit charge when it moves from one point to another. So essentially we can think of the electrons gaining potential energy as they the ones coming into this side of the battery compared to the ones coming out. They have a higher potential energy. They have a higher potential to do work as they move through the circuit. And it's just really important to keep that definition in mind, that the potential difference across a battery, or as we'll see later across a resistor, it's the amount of energy per unit charge, per coulomb. Of course, again, its units are, we've seen this before, joules per coulomb or volts. Of course, this potential difference also indicates the amount of, it's a measure of the push there is to push these electrons around the circuit. So for a high potential difference, that's kind of looking at a high electric field from one end to the other, there's a bigger force per charge to push electrons through this circuit. If we assume that this wire is almost a perfect conductor, we actually get no energy loss as the electrons move through that perfect conductor. So when we look at where that energy is actually lost in the system as it goes around the circuit, it actually is dissipated, so turned into another form of energy like heat in the case of the resistor. That transformation from potential energy of the electrons to the kinetic energy and the heat that's generated happens at the resistor only, and not within the wires. So if we go back and make it even more confusing and think about conventional current, and just imagine for just a moment that we've got positive charges flowing the opposite direction to the electrons, we would actually get an increase in potential as we go from the negative terminal of the battery to the positive terminal. The potential will be the same along here, so there'll be no potential difference anywhere in the wire, and over here there will be a loss of potential as we go from one side of the resistor to the other. So as we move from one side of the battery to the other, we get a positive. We go from one side of the resistor to the other, we get a negative potential difference. And if you think about it carefully, the same thing will apply if you just define the direction of electron flow. But we won't worry too much about that now. Just all you need to know is that you get an increase in potential across the battery and a decrease in potential across a load. We could put into this circuit an ammeter. Oops, I've just lost part of my circuit here. We could put an ammeter in here and measure the current. Now it doesn't matter where we put this ammeter. We could put one here on this part or across this top part of the circuit here. It doesn't matter. The current or the rate of charge flow through those wires, and in fact through the resistor, will be the same no matter where you are in that single circuit. We're talking about a series circuit here where there's just one path through the circuit. The current will be the same. And the current, of course, which we have seen before, is defined as the rate of flow of charge. So essentially the amount of charge in coulombs passing a point every unit of time, so every second. So this would be coulombs per second, or amps, which we give the symbol of A. And this is the same throughout the circuit. The resistor that I've referred to here, which we're going to look at what defines resistance a little bit more in the next video. But a resistor, just by way of introduction, provides resistance to current flow. And that resistor provides resistance basically by the nature of the material that's there. The electrons that are flowing might bump into things more often. So it basically slows everything down by way of collisions with the material that makes up the resistor. And if there are more collisions, it means that more energy is being dissipated. So a resistor dissipates the energy that the charges have. They start off with a potential energy, and then they convert that within the resistor to another form of energy, usually heat in the form of when we're talking about just a normal resistor. So I've just got a quick three-part example to talk to you about. I'll just move that up there. So our example is in 1 minute, we have 15 coulombs of charge doing 300 joules of work in a motor. It could be in a resistor or a lamp, it doesn't matter. So the first question that you need to calculate is what is the current flowing in that circuit. And of course all we need to do is look at our definition of current. It's the amount of charge flowing per unit time, and our charge is 15 coulombs. Our time is 60 seconds, which gives us 0.25 amps. So for the second part of the question, what is the potential difference across the motor? So potential difference is the amount of energy lost across the motor per unit charge. So for every charge that goes through there, how much energy is lost. So every coulomb of charge, how much energy is lost. So we have 300 joules of energy, because that's how much work has been done, divided by the amount of charge, which is 15, which of course gives us 20 volts. So we know we have a potential difference of 20 volts across that motor. The last part is, what is the potential difference, or the voltage provided by the power supply? And we know that the voltage provided by the power supply, I'll just write PS there, power supply, is the same as the voltage lost across the motor, because by the time those charges get back, I'll just go back up to the diagram up here, the charges that come out of here lose all their potential energy as they go across this load, and then when they come back to here, they are given again that 20 volts in this case. It's lost 20 volts across here, and so on and so on. It goes around and around. So all the energy that the charges gain across the battery, they lose across the resistor. And this is a little bit conceptually hard to get a hold of, and we'll talk about it more in class. So just down here, the potential difference across the battery is the same as across the motor, so it's 20 volts.